Welcome to presentation about the vehicle detection in the autonomous vehicle environment for potential collision warning. This presentation consists of 6 main parts. In the first topic, I would like to make a little introduction about ADAS and ROS. Advanced Driver Assistance System (ADAS) are electronic systems that assist the driver while driving. The purpose of ADAS system is to increase passenger safety and road traffic safety. The main task of automated system that ADAS provides is to reduce the human error possibility. Object detection algorithms in camera-based imaging use two approaches. The first one is using traditional computer vision techniques, while the second approach is using deep learning methods. Robot Operating System (ROS) provides all the software support needed for the implementation of ADAS algorithms and enables the writing of real-time algorithms. The next topic is related work. In first paper, algorithm detects vehicles and estimates its distance using HAR features to determine whether the image from camera contains an object of interest. Two methods of distance estimation have been developed. In second paper, the real-time vehicle detection and monitoring method using deep neural network is presented. The network was tested and it's shown that the network had an average precision of 80.5%. This solution shows that deep neural networks are more efficient and better solution for object detection in comparison with conventional computer vision-based methods. In third paper, vehicle detection and distance determination based on monocular camera is presented. This algorithm is based on the Yolo-Jones object detection algorithm. Yolo-Jones algorithm is a machine learning algorithm for object detection using HAR feature. In the next topic, I will talk about the proposed algorithm. The proposed algorithm consists of 4 nodes: camera node, Yolo V2 node, distance assessment node for real-world images, Carla simulator distance assessment node. Camera node accepts the input image from the camera and forwards the frame by frame to the Yolo node. The Yolo node forwards the detected vehicle class, the coordinates of the detection bounding box, and detection confidence to the nodes for distance assessment. One node is used for the real-world image, while the other is used for the Carla simulator images. The most important part of the distance assessment algorithm is detection of vehicles. The Yolo V2 algorithm used in this paper is just to detect 4 classes of objects: car, van, bus, and truck. After collecting the images, each bounding box is marked for the objects of interest in each image respectively. Before training the Yolo algorithm, the Yolo configuration file settings were changed to detect the desired 4 classes of objects. In right table, we can see the number of objects per class that we used for training of Yolo 2 algorithm. The parameters that needs to be set before training is batch 64, subdivision 32, num2, and last filter 18. The meaning of these parameters is presented in the next slide. Batch parameters say how many images will be loaded for one training iteration. Subdivision parameter determines in how many mini-batches will batch be split. The size of the last filter in Yolo V2 network is calculated by the next equation. The classes parameter determines how many object classes the algorithm will detect. The num parameter is selected based on the size of objects to be detected. This parameter tells us what is the maximum number of possible detections within a single cell of 1313 matrix. As initial network weights for training Yolo V2 algorithm, the dark 53 weights are used. The minimum number of training epochs is calculated by the next equation. The minimum number of training epochs of Yolo V2 algorithm is 16,000, and therefore in this paper the Yolo V2 algorithm has been trained up to 20,000 iterations, since the mean loss after 20,000 iterations has dropped below 0.5. The training lasts about 26 hours. As we said, proposed algorithm have 2 nodes for distance assessment. First, we will talk about distance assessment node for real-world images. As input, it uses the parameter obtained from Yolo V2 algorithm. Based on the object class, algorithm determines which vehicle reference width will be used, due to the fact that each vehicle class has different width. The distance is estimated by following equation. In the equation, f represents focal length of the lens in millimeters, w indicates the width of the real-world vehicle in millimeters. W image indicates the width of the video frame in pixels. W object indicates the width of the object in the video frame in pixels. W camera indicates the width of the camera sensor in millimeters. The second node is Carla Simulator Distance Assessment node. This node is used for distance assessment in Carla Simulator. Reference vehicle width was obtained by taking samples of the vehicles in the simulator distance of 5 to 50 meters in steps of 1 meter, and looking at the width of vehicle in the image elements at each distance. After the experimental calculation of the vehicle width and distance of 5 to 50 meters, a reference table was created and used to determine the distance from the camera to detected vehicles. In Carla Simulator, if the vehicle is on distance smaller than 10 meters, the camera doesn't capture the whole vehicle, and in order to have sufficient number of cases of too small distance, the node was tested with 12 meter settings. These two images represent output of the algorithm. As we can see, there is a bounding box around vehicle with name of a class of detected vehicle and estimated distance. There is also a message that is printed on a screen in case of a too small distance. In the next topic, I will talk about testing of the proposed algorithm. For the test purpose, darkened environment is used. All test images from real world were taken with the camera of Huawei P10 Lite mobile device. The test image for Carla Simulator were taken with the embedded Carla Simulator camera. The test set consists of two parts, a test set for the testing the Yolo V2 node and test sets for testing nodes for distance assessment. The accuracy of an object detector is determined by the intersection of union values, which tell us how much the average detection boundary box matched the actual bounding box that was marked during the creation of the test set. During the testing of Yolo V2 node, the number of true positive detections, the number of false negative detections, and the number of false positive detections were monitored. From the monitored parameters, recall, precision, and F1 score were calculated. As we can see in the table, algorithm detects car class objects the best. This table represents test results for Yolo 2 algorithm detection for fog and rain. Table on this slide represents test results for Yolo 2 algorithm detection for night and sun. If we compare all of these results, we can see that Yolo 2 algorithm works the best for sunny conditions. Also, algorithms have problems with detection of objects in conditions of poor visibility. The reason for the lower detection in night driving conditions is due to the lower illumination, while in the rainy conditions the problem arises when the droplets of rain hit the glass in front of the camera, which makes a big change in the image itself. In foggy conditions, the algorithm performs better at smaller distance, while detection at lower distance causes problems because vehicles are not visible in fog. The algorithm shows the best result in sunny conditions. Algorithm best detects car and vans while it has weaker detection of trucks and buses. The improvement of Yolo V2 detection is possible by expanding the training set with more images and retraining it. On this slide, we can see results of testing distance assessment for the car and van class for the image from real world. It can be seen from the table that as the distance from the detected object increased, the accuracy of the estimated distance decreased. These two tables represent results of testing distance assessment for the truck and bus classes for the image from real world. The average intersection over union for the test image set for real world image is 64.24%. The evaluation was performed on image of 4 classes of objects at distance of 5 to 45 meters. It was determined that the Yolo V2 algorithm does not detect objects further than 45 meters away. The reason for not detecting objects more than 45 meters away is because Yolo 2 algorithm is trained on 416.416 images. This problem could be solved by training the Yolo V2 algorithm on large images. By increasing the distance of the detected object from the vehicle camera, the deviation of mean value from the actual value of the distance of the detected vehicle also increases. At larger distance, the variance in the size of bounding box in the image elements are lower and therefore the distance estimation error increase. The estimated distance is always less than reference distance, because the error introduced by the difference between the reference and defined bounding box and the error entered by the vehicle's predefined reference width reduce the estimated distance. The table shows the test result for distance estimation for the car class in Carla Simulator. Distance assessment is performed on test sets of images consisting of 5 different cars at distance of 10 to 50 meters. Yolo V2 algorithm does not detect objects further than 50 meters away. The reason for not detecting objects is that in the simulator, objects become very small and blurry after 50 meters. Detecting bounding box deviates from the reference bounding box, which introduce an error in the distance assessment. The average intersection of your union for the test image set is 59.48%. The next topic is conclusion of this paper. The proposed method uses Yolo v2 algorithm in order to detect surrounding vehicles in image from camera. Output parameters of Yolo v2 algorithm are used to determine distance for detected vehicles. Algorithm runs at an average of 40 fps. Proposed method allows detection of objects even when only part of an object is inside an image, or when multiple objects overlap. There are possible improvements that could make algorithm work better. In the next topic, I would like to answer on few questions. Can you provide insight into overall safety verification when introducing diversification via an additional set of sensors? How would this approach be integrated into your work? Adding an infrared camera would increase the detection accuracy of objects in poor visibility conditions, such as fog, night, and rain. Also, using a long-range radar system would increase the accuracy of estimating the distance of detected objects. Using more sensors would increase the security of the system itself, because when one of the sensors fails, the system could work relying on one of the remaining sensors. Can you discuss automotive middleware solution and fitness of your solution to be applied utilizing various middleware APIs? ROS Robot Operating System has been built on top of an existing middleware solution DDS. Data Distribution Service for Real-Time Systems. DDS is an object management group machine-to-machine standard that aims to enable dependable, high-performance, interoperable, real-time scalable data exchange using a publish-subscribe pattern. ROS aims to support multiple DDS implementations despite the fact that each of them differs slightly in their API. Since the solution was developed in ROS, it is possible to use the built-in middleware API. I would like to thank you all for your attention.